Hi, Sydney. It's Miss Pierce. We miss you. I hope you get back soon. I hope you're feeling a bit better. I sent you some videos to look at when you feel like getting caught up a little bit on gas law properties of gases, and some of the when you change the pressure of a gas, what happens to volume, things like that. This man, Tyler DeWitt, does a really good job of explaining some of those basics, so I thought you could watch that first. And then to work the problem sheet that I sent, we're going to make a list of the variables. So if we were doing number 1 on the sheet, that the title is Boyle's, Charles, and Combined Gas Problems, we make a list of the variables. There's a V1, that's the initial volume of the gas. P1 is the initial pressure of the gas, and T1 is the initial temperature of the gas. And then you could change one or more of those conditions and see what happens to the volume. So the new volume is V2. Whatever the new pressure is P2. And T2 is the new temperature. So usually the initial values are given to you in the problem first, in the first sentence. So if you look at number 1, it says picture some oxygen in a balloon. Some oxygen has a volume of 150 milliliters. And that little dot behind the 0 means that 0 is a significant digit. So 3 significance total. So that's our original volume of the balloon. The outside air pressure pushing down on that balloon, or pushing in on that balloon, is 720 millimeters, and there are 3 different pressure units you can use. This one's using millimeters. They want to know how many milliliters would the size of the gas balloon be if you change the pressure to 750 millimeters. And so we're not using temperature in this problem. So temperature must be staying constant. So we're not changing the temperature of the outside. And what's happening in this example is the pressure from P1 to P2 is going from 720 to 750. So our pressure is going up. If the pressure, if you take a balloon filled with oxygen gas and you squeeze on the outside, so you're increasing the pressure, you can squeeze it into a smaller space. So we would expect the volume to go down at the end of this problem. So when we find our V2, we would expect that the V2 would be smaller than the V1. So our equation for the combined gas law is this: V1 times P1 over T1. And then you have all the 2's, all the new values on the other side. And then you just kind of take out whatever you don't need. We said we didn't change the temperature. Either they won't give you the temperature or they'll say it's held constant. And then so you just take them out. So our equation is just going to be V1 P1 equals V2 P2. So you would plug in the numbers that you have for those in those places. So you'd have 150 mils times 720 millimeters equals whatever the new V2 would be times the 750 millimeters, that higher pressure. And so all you have to do to solve is you would divide both sides by 750 millimeters. So it would cancel on this side. And so your V2, your new volume, would be whatever you get when you divide those 3 numbers. And so we would get 144 milliliters. So that would be our answer. That's the V2, the new volume when you increase the pressure. So we found that we went from P1 to P2. We were increasing the pressure, squeezing on the balloon, and the volume did become smaller. It went from 150 mils to 144 mils. So we did decrease the volume. And so you can do this with these other problems that you have here. Might change, leave the pressure the same and see what happens to temperature. So in some of these problems we'll change the temperature, see what happens to pressure or volume. You could solve for any of those 2 variables. We do have to be careful not to use Celsius temperature, because there are some gases that become gases from solids or liquids. They turn into a gas. So one thing about temperature, we do have to work temperature in terms of a unit called Kelvin, because there are some gases that are gases at negative temperatures. And so if we put negative temperatures into that equation with the 6 variables, we'll get a negative volume, and that just doesn't make any sense. So we convert to a Kelvin scale by taking the degrees Celsius and adding 273. So if you had a temperature of 20 degrees Celsius, we would call that 298 Kelvin. So one thing you have to remember about these gas laws is if we work in temperature, if we use Celsius, There are some gases that become gases at negative temperatures. And if we plugged in a negative number for one of those T's, T1 or T2, we would get negative volumes or negative pressures, and that just doesn't make sense. So we have to work in a unit called Kelvin. And all we do is we take the Celsius temperature and we add 273. So if we had a 20-degree Celsius temperature, we would add 273, and we would say that that temperature is 298 Kelvin. And this way, if the coldest possible temperature that exists is absolute zero, so that's negative 273 Celsius. So if we add 273 to that, the coldest possible temperature is 0 Kelvin. So if you work in Kelvin, you'll never have any negative numbers, and everything will work out kind of nice. So whenever you have a T, make sure you convert it to Kelvin first, and then you can plug it in for T1 and T2.